Alternating series. An alternating series is a series whose terms are alternately positive and negative. Here's an example where we start out with a positive, then it goes negative, positive, negative, positive. Here we start out with a negative and it goes positive, negative, positive, negative. In general, just knowing that the limit as n approaches infinity of a sub n equals 0 tells us very little about the convergence of the series. However, it turns out that an alternating series must converge if its terms consistently shrink in size and approach 0. So if we have a sequence of positive values, you can't ruin the fact that this is alternating, then an alternating series converges if both of the following conditions are satisfied. 1. The limit as n approaches infinity of a sub n is equal to 0. In other words, it passes the nth term test. So passes the nth term test. A sub n is a decreasing sequence, meaning that the term before is greater than the next one. So the next term is less than the previous term for all n. Note this does not say that if the limit as n approaches infinity of a sub n does not equal 0, the series diverges by the alternating series test. The alternating series test can only be used to prove convergence. If it fails the nth term test, then we say diverges by the nth term test, not by the alternating series test. This diagram down here shows what's happening with an alternating series. So you start out with s sub 1, and then the partial sum, and then you add the second term, and it's less than what it's converging to. For example, the alternating harmonic series converges to natural log of 2, but it does it by being greater than that value, then less than the value, and then greater, to there, and then less than, and then it's greater than the value, and it alternates back and forth, greater and less than the value, but it gets closer and closer as we add on more terms. Determine whether the following series converges or diverges. So step 1 is we do the nth term test. We have the limit as n approaches infinity of n over 2n minus 1. That's equal to 1/2. That is not 0. So we say diverges by nth term test. Here we have the limit as n approaches infinity of n over natural log of 2n. Well, here we have, this is the natural log of 2n, and that's n. So this is headed to infinity, which is not 0. So again, we can say diverges by nth term test and not by alternating series test. If you don't know what's going on, if you don't quite know what's happening here, we can always list a few of the values of the terms out. So if we plug 1 in, cosine of pi is negative 1, and we have over 1. Then cosine of 2 pi is positive 1. Cosine of 3 pi is negative 1. Cosine of 4 pi is positive 1. And so we have, we can write this as n equals, we can go from 1 to infinity of negative 1 to the n over n. Now this is the alternating harmonic series. So we can say limit as n approaches infinity of 1 over n is equal to 0. So it passes the nth term test. And we can confidently say that 1 over n plus 1 is less than 1 over n, because if you hold the top constant and you have a bigger denominator, the bigger the denominator, the smaller the value. So we can say converges by alternating series. And that's the only time I'll do that test for the alternating harmonic series, because now we can say, instead of all that, we can say converges by alternating harmonic series. Here we have the limit as n approaches infinity of n over n squared plus 10. That's equal to 0. So this passes the nth term test. But we have to be able to say n plus 1 over n plus 1 squared plus 10 is less than n over n squared plus 10 for n greater than what value? So we don't have to have a sequence that decreases right away. It can eventually decrease. So when does it start decreasing? Well, this is a little too complicated to just be able to look at and tell when this starts decreasing. So what we're going to do is we're going to let f of x equal x over x squared plus 10, not 2 squared, x squared plus 10. We're going to take the derivative, which is bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom, and that's going to be over the bottom squared. And so the top becomes 10 minus x squared, because x squared minus 2x squared is negative x squared, over x squared plus 10 squared. Well, we want to know when 10 minus x squared becomes negative, because that would be that would have a function that has a negative slope, and functions that have negative slopes are always decreasing. So negative x squared less than negative 10. So x squared greater than 10. So x has to be greater than the square root of 10. And then after that happens, once that's bigger than the square root of 10, this will always be negative. So we'll always have a decreasing function, therefore a decreasing sequence. Now, n, that's integers. So it doesn't make sense for n greater than the square root of 10. Square root of 10 is 3 point something. So for n greater than 3, we have a decreasing sequence, and we can say converges by alternating series test. Alternating series remainder. Suppose an alternating series satisfies the condition of the alternating series test, namely that the limit as n approaches infinity of a sub n is equal to 0 and a sub n is a decreasing sequence. If the series has a sum, then the remainder, or the error, is equal to the exact value minus the approximation. That's less than what we say is the first omitted term, where s sub n is the nth partial sum of the series. In other words, if an alternating series satisfies the condition of the alternating series test, you can approximate the sum of the series by using the nth partial sum, s sub n, and your error will have an absolute value no greater than the first term left off. Approximate the sum by using those first 6 terms and find the error. Use the results to find an interval in which s must lie. So let's get the first 6 terms. We have a positive 1 over 1 factorial, and then minus 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, 1 over 5 factorial, and finally minus 1 over 6 factorial. And I think I've already added that in the calculator here. I was trying to arrow over, but yeah, that'll work. We get 0.6319 and then a whole bunch of 4s. So that's the approximation. So we're approximating the sum. Find the error. Well, the error is going to be the first term left off. So the error is going to be less than 1 over 7 factorial. Actually, the absolute value of that, which is equal to 0.001984126984. Now, if we're going to find an interval in which the actual sum must lie, then we take the approximation and minus the error. That's what it could be to the left, which is that 0.63. So 0.6317, 460317. That's less than the sum. And if we take the approximation and add on the most error we could have, and I accidentally subtracted, then I redid it all the way down at the bottom here, all the way down at the bottom. Let's get down there. So now when we add on the error, then we get 0.6321428.571. Now this number right here, this is called the upper bound. Upper bound. This is not called the upper bound. This is just the highest value that the actual answer could possibly be. Approximate the sum of this with an error less than 0.001. Well, if we plug 1 in, that's going to be a positive. So 1 over 1 to the 4th, of course, is 1, minus 1 over 2 to the 4th. Let's go one more. Plus 1 over 3 to the 4th. Let's see, what did I do on the calculator here? I got to go all the way back up to the top now. All the way back towards the top. I started with 1 over 4 to the 4th. So if we added these three up and we said, well, this is our maximum error, the first term left out, then our error would be 0.003, but that's not less than 0.001, that's more. So what if we added all 4 of these and said 1 over 5 to the 4th could be our possible error? Well, that's not less than 0.001, that's slightly more. It turns out 1 over 6 to the 4th. So if we added up these 5 and then we said, well, this is our error, then we'd have an error that's less than 0.001. So when we add up all 5 of those, which I think I've done here, approximate the sum. So the sum of 94753, 9429 has an error that is less than 0.001. Because this is the maximum error you could possibly have. This is the upper bound, we call it. The Maclaurin series for the natural log of 1 plus x is given by this. On its interval of convergence, this series converges to natural log of 1 plus x. Let f be the function defined by this. Write the first 4 non-zero terms and the general term of the Maclaurin series for f. Well, let's replace all the x's with x over 3. So if we replace x with x over 3, we get x over 3 over x squared over 3 squared times 2 plus x to the 3rd over 3 to the 3rd times 3 plus x to the 4th over 3 to the 4th times 4 plus keep on going. And the general term. We're not done yet, though. We're going to multiply all that by x. So x squared, x to the 3rd, x to the 4th, x to the 5th. And then we'll write in all the other stuff. So plus dot, 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 plus, what should we start with? Should we start with 1? So we're going to go, let's see, that was plus minus plus, plus minus plus. This should have been a minus. That should have been a minus because it's alternating. So if we start with 1, we have negative 1 to the n plus 1. If we're going to start with 1 over 3 to the n times n and x to the n plus 1. Determine the interval of convergence of the Maclaurin series for f. Show the work that leads to your answer. We have to do interval of convergence. Limit as n approaches infinity, absolute value of x to the n plus 2 over 3 to the n plus 1 times n plus 1, and then times 3 to the n times n over x to the n plus 1. So x over 3, limit as n approaches infinity, times n over n plus 1. So we need the absolute value of x over 3 to be less than 1. So negative 3 less than x less than 3. Interval of convergence is negative 3 to 3. Let p sub 4x be the 4th degree Taylor polynomial. For f about x equals 0, use the alternating series error bound to find an upper bound for the error on the 4th degree. So here's the 4th degree. So the error is less than absolute value of x to the 5th over 3 to the 5th times 5, but that's really 2 to the 5th because we're using 2. So that's equal to 32 over, let's see. Oh, I was looking, I need to look right here. I kind of looked at the wrong one. This is actually 3 to the 4th times 4. So 81 times 4. That's 8 over 81 is your upper bound. Determine whether the following series converge or diverge. We have the limit as n approaches infinity of n over 3n minus 1. That's 1/3, which is not 0. So we can say diverges by nth term test. Here the limit as n approaches infinity of 1 over square root of n, that is equal to 0. And 1 over square root of n plus 1 is less than 1 over square root of n. So converges by alternating series test. Here we have limit as n approaches infinity of n over n squared minus 1 is equal to 0. So that passes the nth term test. But now we have to be able to say n plus 1 over n plus 1 squared minus 1 is less than n over n squared minus 1 for n greater than what? So we're going to let f of x equal n over n squared, actually x over x squared minus 1. So f prime of x is equal to bottom times the derivative of the top minus top times the derivative of the bottom over the bottom squared. So we need negative 1 minus x squared to be less than 0. Well, I mean, you could do this. You go negative x squared less than 1, x squared greater than negative 1. Well, x squared will always be greater than negative 1. So for n greater than or equal to 1, we have a decreasing sequence. So converges by alternating series test. Find the power series representation for 3 over 4 plus x centered about x equals 2. Well, f of x is equal to 3 over 4 plus x minus 2 plus 2. And that's 3 over 6 plus x minus 2. So we have it centered at 2. Now we need that to be a 1. So 1/2 over 1 minus negative 1/6 times x minus 2. So now a sub 1 is equal to 1/2, and the r is equal to negative 1/6 x minus 2. Find the power series representation. So 1/2 minus 1/2 times 1/6 times x minus 2 plus 1/2 times 1/6 squared x minus 2 squared, and then minus 1/2 times 1 over 6 to the third times x minus 2 to the third, plus keep on going. Find the radius of convergence. Well, the absolute value of 1/6 x minus 2 has to be less than 1 because this is geometric. So negative 6 less than x minus 2 less than 6. So radius of convergence is equal to 6. Use the third degree Taylor polynomial to estimate f of 2.1. So p sub 3 of 2.1 is equal to, I think I typed this in the calculator already. Where's the, I got to look for the 1/2. There we go. It ends up being 0.4918032407. I did that by plugging 2.1 in for all of these x's and typing it into the calculator. What's the maximum error in the third degree estimation? So r sub 4, the absolute value of r sub 4, that's less than, let's go with absolute value of, we have 1/2 times 1 over 6 to the fourth, x minus 2, actually 2.1 minus 2 to the fourth, and that is equal to, I think I did that right here, I hope anyway, 1/2, 1/6 to the fourth, 0.1 to the fourth. Yeah. And so the maximum possible error is 0.00. Oh, how many? How many do we have? Oh boy. 1, 2, 3, 4, 5, 6, 7, 3, 8, 5, 8, 0, 2, and keep on going. Find the actual error and compare it to the predicted maximum error. So the actual error. Well, here is the estimate. And then if I plug 2.1 in for here, that'd be the actual value. So there, right there, that is the actual error in the approximation. So the actual error is 0.023456793798852, which is smaller than what we call the upper bound. That's the upper bound. That's the maximum error we could possibly have. Give the first 4 non-zero terms in the general term for the series for the function. Let's go with cosine of x is equal to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus keep on going. Cosine of 3x is 1 minus 3 squared x squared over 2 factorial plus 3 to the fourth x to the fourth over 4 factorial minus 3 to the sixth x to the sixth over 6 factorial plus keep on going. Now we're going to multiply everybody. How about we multiply everything by -2? So -2 plus all this stuff. 2 factorial. I need a 2 times. 2 times 3 to the fourth, x to the fourth over 4 factorial. What I multiply by? -2. That'll be plus. This will be minus. That's be minus. Plus 2 times 3 to the sixth, x to the sixth over 6 factorial. Keep on going. And then 2, then we're just going to add 2 to all this. All right, so we're adding 2. So that removes that. So we have this. First 4. Plus 2 times 3 to the sixth, x to the sixth over 6 factorial minus 2 times 3 to the seventh, x to the seventh over 7 factorial. The general term, what should we start with? 2, 4, 6. This should be, what should this be? 8? Not 7, but 8. So 2, 4, 6, 8. Let's start with 1. We got 2 times 3x to the n plus 1 over 2n factorial.